when I first learned the concept, the idea that came to my mind was, suppose that you're on a trip and maybe you're watching it from a helicopter. Maybe you're on a safari and you're watching a herd of buffalo. Okay, so that's like a very lazy drawing of the buffalo. Now, the buffalo are prey animals, right? And they like to congregate. They like to be bunched up together. Cows like to be bunched up together. And sheep like to be bunched up together. And since I'm not one of those, I hate going to parades, and I hate New Year's parties when they go to Manhattan, because I feel like I'm inside of an open set. Now, what is an open set? Okay, so why do cows and sheep and cattle, why all those creatures like to bunch up together? They don't want to be eaten, right? And one of the nice defenses, so in this case, let's imagine that the cattle are two-dimensional creatures. If they are two-dimensional creatures, within their space, the only place where they can be attacked are from all the directions on the plane. They cannot be attacked from above. Okay? So the cow that they see, so I'm looking at it from the helicopter, I'm looking at the microscope, and I look at this cattle, and it looks to me, well, this one is feeling itself very safe. Nobody's going to attack it because everywhere you look, it's surrounded by other cattle. Okay? Everywhere you look, it's surrounded by other cattle. Now, which cows are in danger? Those that are at the periphery, right? So if this were the herd, so this cow can be attacked, this can be attacked, all the ones at the periphery can be attacked. Now, what would be the ideal of our herd structure? A structure that protects all the cattle at once. What must be true about this structure? Yes?
No cows are on the periphery.
No cow on the periphery. No one's outside. You understand? There might be a periphery, but somehow, no matter at which cow you look, the cow is completely surrounded. It's protected by a bodyguard of other cows. So you can think of maybe cells, maybe bacteria cells. One bacteria cell is protected by a crowd of other bacteria, and no matter which bacteria you look at, it's defended. Make sense? And that's going to be how we that's actually, in some sense, the purpose of open sets. They are supposed to defend the herd. There, for example, you might have a curve, and in complex analysis you have a curve, and you want to defend it against singularities. Singularities are bad, so you want to defend it against singularities by an open set. Okay? So maybe a function has a point where it's differentiable, but maybe near it there are very scary bad points where it's not. So does it have protection from those bad non-differentiable points? Open sets are supposed to give protection. Good? So let's make this definition formal. So definition. So let MD be a metric space. Okay. MD is a metric space, and then we will say that a set G, which is a subset of M, is open if, now, so this is a G, so that's my herd. That's my set of cattle. Open means ideal. In other words, no element is on the periphery, no element is facing danger. Everybody is surrounded, every cow is surrounded by a bodyguard of other cows. So how can you express that mathematically? What does it mean that it's surrounded by other cows? If any x belonging to, if I should say like this, if for any x belonging to G, there is epsilon bigger than 0, such that what? Can you see what I'm getting at? So the picture is this. So we have this point x. And how do I determine that this one member of the set is protected? Well, I can take a target. Okay, so I take a target, and this guy within a target of radius epsilon, so that's my epsilon. Everything I see in this target are members of G. Okay, such that the ball of radius epsilon centered at x is an entire subset of G. Okay, that means that within this vicinity, every point is just a point of G. So that's my ball of radius epsilon around x. This is x. Make sense? So there you can think of them as points. So the entire space is either occupied by points of G or points that are not in G. So an open set does not allow any of its members to be directly in contact with points that are outside of the set. So it means that every x is protected against members of G complement. The reason I use the word G is for Gebiet. So that's the German word for region. Okay. All right. So let's consider examples. So first of all, in any metric space, the whole space M is open. Do you see why? Why is M open relative to itself? Take M, right? M is the full region. So take any point and take any ball of any radius. Automatically, by definition, right? So by definition, that ball has to be inside of M. Do you see why? Because x belonging to MD means that the ball of radius r, where r is any number around x, this is just the set of all y such that the distance from x to y, so it's the set of all y where? The set of all y in M, right? Where else? That's the full space. In M, such that the distance from x to y is less than r. Okay? And that automatically implies x is an element. So it automatically implies that the ball of radius r around x is a subset of M. There is nothing to think about, right? The structure is picking only elements from M, so what else can it be? So automatically, any space is open relative to itself. B, and I should also mention, also, empty set is open. Can anybody tell me why empty set is open? Everywhere. So M is open and the empty set is open.
Is there no members in it?
Do you see why M is open? Yes? M is open. Well, what's the definition of open? Pick any element of X in that set. So a set G is open in M if picking X in G implies that there is a full neighborhood of bodyguards protecting this X that are all members of G. Now if I take G to equal M, by definition I can take around any X, I can take a ball of any radius. Automatically that ball is only containing elements of M. There is nothing else to contain. So why is the empty set open?
Because there are no members. Everybody's protected because there is nobody.
Right, it's like an inspection comes to town and you say, well, can you show me who is not protected? Right, there is nobody to show.
No.
Okay? There is no evidence of a single member of the set that could be harmed. Okay, so now example B. In R, any open interval is an open set. So very simply, if you take an interval, this is an interval from A to B. Now so you understand when I say an open set, I mean open relative to R. In other words, in R, it's one-dimensional space. The only places you can be attacked are from the left or from the right. Which means that if I pick any element X in the set, so I pick, let's say, I pick this point. So this is my X. I need to show that there is a ball of some radius that is fully contained in the set. So what can I do? For the X I picked, I can pick this as one of its wings, and then I just copy the symmetry. I pick the nearest point, the nearest endpoint, and I make it the radius of my ball. Okay, so what you do formally, what this means formally is that for X belonging to the interval AB, pick epsilon to equal the minimum of the absolute value of X minus A, or you don't need absolute value here, it's pretty clear that X is between them, so you can just say pick minimum of X minus A and B minus X, right? Then the ball of radius epsilon around X, which equals to X minus epsilon x plus epsilon will be a subset of the interval AB. You see, in this case, the minimum was the distance from A to x. Make sense? So you can say that the case where A equals to minus infinity or B equals to infinity are similar, are even simpler. You might say that if it's infinity, that the minimum is always the other guy. Okay? So if I extend B to infinity, then I always pick A as my edge. If I extend B to minus, so A to minus infinity, then I always pick B as my edge. So that's not a problem. So C. Well, so if we mentioned it, so what about example C? In R is the closed interval 0, 1 open? Is it open? What's wrong with it?
At 0, it's closed.
At 0, well, no, what's the problem? So, what I'm asking, in other words, I'm asking, is this herd protecting? Is this a perfect herd for all the members? So, what makes it not perfect?
0 is not.
0, right? The answer is no. 0 is not protected. And by that I mean that if I take any ball of radius epsilon centered at 0, that will contain minus epsilon to epsilon. It's never inside of the interval 0, 1. Okay? So no matter how I try, I cannot protect 0 from the left. So now D. If we have a discrete metric space, what do we know? We know that ball of radius 1 around x, how many points does it contain? So I have some m, and I use the discrete metric. So what's the ball of radius 1 around x? What is that? No, because it's less than 1. It's 1 point, right? You took it less than or equal, but it's always less than, okay? If you do the closure, then it will be m, right? So that would be simply the singleton x. Okay? What does it mean? It means that every single point, by this definition, every single point is its own protector. So what does this mean? This means that every subset of MD is open. Do you see why? Let me just make sure. You tell me why. Why does it mean that every subset is open? Yep.
Because if you take a bunch of points for each one, you can construct an open ball, which is just the same.
Right. Here is how you verify that the set is open. You look at each member in the set and ask, is this member protected? So I pick a point, whatever collection I have, I point to X. How am I going to ensure it's protected? I just pick a ball of radius 1. By definition, that's enough. If I pick a ball of radius 1, clearly it's going to only contain 1 point, so automatically it's protected. Do you understand? you can use the same radius 1. Protect each of them by a bubble of radius 1. And since that bubble will just contain the point, you know that the set is already automatically protected. Okay? Everybody, it made sense to everyone? Yes? So protection is like a bubble wrap. So you take a member and you need to enclose it in a ball. And inside of this ball, members outside of the set are excluded. So how small is the ball doesn't matter. I can make the radius as small as I like. So if I make, in this case, if I fix the radius to be 1, the bubble only contains 1 point. So everybody is automatically protected. All right. So let's begin proving a few basic results about open sets. I'll keep the definition for a moment. So proposition. Let M be a metric space. Then every open ball of or any open ball in M, I don't know, in M is open. So I purposefully wrote this statement in this form because it's confusing, right? Every open ball is open, no big deal, right? Isn't it called open ball? But think about the definition, okay? So proof. So open ball means some ball of radius r around x. And what is this? This is simply the set of y belonging to M such that the distance from x to y is less than epsilon. So nothing in the statement makes it open. Okay, so open ball is like a noun. Just erase the space. Open ball is a noun. And when you say something is open, it's like you're saying open balls are perfect herds. It's a perfect herd set. In other words, an open ball is a perfect arrangement for members of the herd to protect themselves against predators. Make sense? So open ball open means this herd is in perfect arrangement to defend itself against predators. No predator can eat any members of that set. Yep.
But that does prove it's open.
So I need to prove that it is open. Okay? So here we go. So we pick the point x and we have this point x. And we have its radius is epsilon.
Professor, the definition does prove it's open because for it to not be open, then the distance from x to y has to equal epsilon.
Well, what the definition proves is that x is protected. X is protected by the full ball. Okay, but does it show that every other guy is protected?
Yes, because the only ones that wouldn't be protected hypothetically would be the ones whose distance from x to y equals epsilon.
How do you know? And I drew a circle. In other words, I drew the ball in Euclidean space. The shape could be very weird. It might not even be possible to visualize the shape. So this is claiming about all metric spaces, any distance whatsoever, no matter how exotic. So what you do is this. So you pick a y. How do you investigate if the herd is in perfect arrangement, so that no members can be preyed upon? So what you do is I point to an arbitrary member and I ask, can I draw a ball around that member that is inside of the big ball? That's what I'm doing, okay? So when I verify any set, no matter what the shape, I just point my finger to any of the members. I kind of take my scope and I aim it at any guy in any head of cattle in this member, and I make sure that the target only contains cattle and nothing else. Make sense? So what I do is I look and I select a Y. This is my Y, and my goal is to show that there is going to be a full protecting neighborhood. It's going to be this thing. Okay? The question is what delta to pick. So this will have radius delta. Okay? So pick Y belonging to ball of radius epsilon around X. We need to show that there's a delta bigger than 0 such that the ball of radius Y around, the ball of radius delta around Y is entirely contained in the ball of radius epsilon around X. Make sense? This is the picture. So X is protected if there is a ball around X that only contains members of his family. But so we know X is protected, but maybe other elements are not protected. So I pick Y and I verify it's protected. So how do I do this? So if I picked Y in the ball of epsilon, so that means the distance between X and Y is equal to epsilon minus delta. It's smaller than epsilon. You agree? So distance. So do I need to write an extra statement? Do you see that it must be epsilon minus some delta for some delta? I'll be more careful. So here, Y belonging to the ball of radius epsilon around X implies that the distance between X and Y is smaller than epsilon, which implies that if I subtract, it's not quite 0. Y is not X, right? So it implies that the distance between X and Y equals to epsilon minus delta for some delta. If delta is epsilon, that means X is Y. So, okay, for some delta. Now we let Z be an element of the ball of radius delta around Y. Then the distance between X and Z by triangle inequality is less than or equal to the distance between X and Y plus the distance between Y and Z. Make sense? So if I pick any Z, that's automatically true. But the distance between X and Y is, so it's exactly equal to epsilon minus delta, and distance between Y and Z is less than delta. So I should say this is strictly less than epsilon minus delta plus delta. You see, this is equality. This is inequality because Z belonging to the ball of radius delta means that the distance between Z and Y must be smaller than delta. So this part is equal, but this part is less. And together it's less, and that is equal to epsilon. Okay? So in other words, that implies that the ball of radius delta around Y because every point in the ball of radius delta around y is a member of the big ball. That implies that the ball of radius delta around y is a subset of the ball of radius epsilon around x. And we're done. And in fact, maybe you would like to notice that the delta we picked is simply epsilon minus the distance from x to y. That's the delta we picked. That's the biggest delta I can pick to be sure that it works. You can see it by the picture. Yep.
Can we also do proof by contradiction? Assume it's not an open ball.
Well, this is the same. If you do proof by contradiction, you essentially go through the same argument, right? Because what do? You pick a point y, and then could this point y not be protected? If it's not protected, there cannot be a small enough
so
radius, right? But if you draw this picture, it kind of guides you. The geometry guides you, and then you try: will the geometry be translated to the abstract inequalities? And yes, it is. So I don't really need this picture. So made sense, guys? So if I ask you on the exam to prove that an open ball is open, that's an easy question. You just kind of can draw this problem and then just say that if you pick this delta, it works. Yeah?
Does the region have to be a circle, or can it be?
Of course not. It could be anything. And it also and this is just an open ball. Just open balls, we are accustomed to view them in this form, but they don't have to be in that form at all.
And the proof would be the same?
Yeah, because that's the point. You see, in the proof, nowhere do I use the picture. It only gave me the intuition on how to set up this problem. What did I actually do? I said y belongs to the ball of radius epsilon around x, and then I decided I pick delta to be this magnitude. If I pick delta to be this magnitude, then I show that this ball is a subset of the ball of radius epsilon around x. How do I do it? Any point in this blue ball by triangle inequality will also be a point in this black ball. That's what I do here. I pick a point, that's Z. If it's in the blue ball, by triangle inequality, it is in the black ball. And that implies that every element in here is an element in here, so that's a subset. Good? Okay. So here is what we can observe. So G is open in M. It's always relative to something. If and only if G can be written as a union of balls of radius epsilon sub x around x, where x is an element in G. So what this is saying is, how do I know that the set is open? Well, I look at all the elements in the set G, each one of them, and each one of them is the center of a ball fully contained in G. Do you understand what this is saying? So automatically, if it's a union, it means each open ball is inside of G. And the reason I say sub epsilon because like in this case, right, this x is protected by a bigger ball than this y. But the way I verify that the set is open is basically each point is the center of an open ball, which in turn is inside of the set. So the full open ball is inside of the set. So the set is built of bubble wraps, of a lot of bubbles. Each guy is the center of a bubble. Nobody is on the outside. So this is trivial. You understand what this means, yes? And another thing that follows, so in other words, open sets are just things that you produce by taking unions of open balls, by taking a bunch of bubbles and grouping them together. So you can imagine, like in this, I imagine this, this toy machine. You put in a quarter and there are a lot of bubbles, right? So the toy is always the center of the open ball. And what you do when you create open sets, you just select a subset of those toys in those spheres. You know what I'm talking about. So you go to a laundromat and you have things like that. Or you had. I never go to a laundromat. I only hear of such things. Yeah. So how much time do we have? I think we have 1 minute almost. That's all. So I will write this theorem, and you think about it, and we will continue next class. So an arbitrary union of open balls is open. That makes sense, I guess, right? Because what you do when you take unions of open sets is just like you're shoveling bubbles.